Hi, we're going to analyze this common emitter amplifier that has a potential divider biasing via R1 and R2, and an emitter resistor via RE1 and RE2. Because of the capacitor CE, RE2 is going to be bypassed, but RE1 will not be. All right. So we're going to derive an expression for the input impedance Zi, output impedance Zo, the voltage gain AV, and the current gain AI. We're going to use the RE model, that's this model over here, to represent our transistor. And we'll just be using basic circuit theory techniques and an algebra. All right, let's start. All right, so as always, whenever we are converting a circuit to an AC equivalent circuit, yeah, this is DC circuit, this is we're going to convert to an AC equivalent circuit, we need to follow these three steps. We should short all capacitors because at high enough frequencies, then the capacitors will have zero impedance, right? So that's the first thing we do. We short all capacitors and we zero all DC sources in this diagram. There's only one DC source, that's VCC. So zero that, meaning it becomes 0 volts. And then finally replace the transistor with the RE model, the simplified RE model that we have on the right here. All right. So let's apply those three principles and have a look at what happens on the output side. Well, C2 is going to be short, so the collector will be directly connected to VO. And since VCC is 0 volts, the top part of RC is going to end up ground. It's going to end up at the bottom. So then RC will be between the collector and ground. All right. So something like this. Okay, so there's ground there connected to there. All right. Let's have a look at the bottom side on the emitter side. The emitter side, when we're looking at the AC equivalent circuit, RE2 will disappear because of CE, right? So CE will short current coming through RE1 straight out through here, CE, and then goes to ground, meaning it will bypass RE2. So RE2 would disappear, but RE1 will remain because it's not bypassed. All right, so it's going to look something like this. So RE1 is connected between the emitter and ground, right, via CE. Okay, and finally on the input side, since VCC is ground, therefore the top part of R1 is going to end up at the bottom, ground, right? And since R1 and R2 shares the same node to base, therefore R1 and R2 are going to be in parallel once we have our AC equivalent circuit, like so. Okay, now let me explain some of the terms that's been added here. So you have the usual VO, VI, ZI, and ZO. So those are the four components that we're trying to work out. You have IO, that's the output current flowing through RC in this direction, right? It's just in the original, that means IO flows into the collector, which is what this is happening here. IO is flowing into the collector. And then you have the current flowing through RE1 as the combination of this current, that's IB on the left branch, and beta IB on the right branch. They merge together through RE1, becoming beta plus 1 IB, such as IB plus beta IB, right? And then on the input side, you have the input current II, so that's still going in. I've lumped R1, R2 together and call it R prime. So this is the parallel equivalent resistor, R prime. And because it's not quite like the other circuit that we had where there wasn't an emitter resistor, since there is one for this case, it's not a straightforward combination of these two resistors. So we need to have another impedance called ZB, B for base. So it's a base impedance, if you like. That means the impedance looking into here, right? Looking into the base. So we need to we need to work out what that is. So the dotted line just simply means that's the interface between ZB looking into the rest of the circuit. All right. So the base looking into the rest of the circuit. So that's what we got. All right. Okay. So as usual, first thing we do is we try and figure out what IO, VO, II, VIs are. All right, so then that can then become a basis for us to work out the four components that we're interested in. So let's look at IO first. So IO is a current that flows through RC going up, going across, because this is open circuit, so it's not going to go through there. So it comes through here, becomes beta IB, merges with the left side, and then comes across here as beta IB, because it has to be beta IB that comes back, right? Because that's what this is. So beta IB is flowing around this loop. All right. So therefore, beta IB is IO. All right. So that's going to be our first equation. All right. So IO is just simply beta IB. All right. All right. So that's our first expression. Now let's have a look at let's have a look at II, but then II is going to involve ZB. So therefore, maybe we should look at what ZB is first. Okay, let's have a look at what ZB is. All right, so this for ZB, we're just basically using, we're going to use KVL, right? So ZB, and Ohm's law and KVL rather. So Ohm's law for ZB, R equals V over R equals V over I. So V is the voltage across here plus the voltage across here. So that's the total voltage across from the top to the bottom, which is also called VI, by the way. Yeah, it's the same node. But here we need to express it in terms of these two components. So we can think of it as the voltage across beta RE plus the voltage across RE1. So we do a bit of Ohm's law here, and then another Ohm's law here, another Ohm's law here, and KVL for the two combined. All right. So let's figure that out. So via Ohm's law, okay. So basically ZB argues V over I. So V here is VI, all right, divided by what is the current that is entering into ZB is called IB, right? So therefore it's just IB there, all right. Now we can express VI in terms of the sum of the voltages across these two components. So let's start with the top one. Well, again using Ohm's law, so V equals IR, so it's IB times beta RE, all right, plus, so that's the voltage across beta RE, plus the voltage across RE1, which is beta plus 1. Or rather, yeah, so just beta plus 1 times IB multiplied by RE1. Oops. Times RE1. Okay. All right. All of that divided by IB. So then we have this expression. In typical discrete component circuits, the value of beta for transistors are typically quite large. They are typically in the hundreds, so therefore beta plus 1 can be approximated to just beta, right? Because it's so much bigger than 1. So let's just capture that. Um, all right, so because beta is typically larger than 1, much larger than 1, so therefore we can write ZB is going to be equal to, okay, so basically I'm just going to copy this. So then this just becomes beta. Instead of beta plus 1, it'll just become beta. All right. And therefore you can combine them. So what you're going to left with is just beta IB times RE plus capital RE1, all divided by IB. So obviously IB cancels out, and what you're going to left with is just beta RE plus RV1. All right. So that's our expression for ZB. Okay. All right. So now we have ZB. Let's figure out what the rest of the components are. So like for II, we can look at II. Now we can express II in terms of IB because basically IB, you have IB entering into ZB, right? So IB enters into ZB. So basically you have the three impedances in parallel. So you have the R prime, which represents R1 and R2, and you have ZB. So all three components, if you like, are in parallel. So you can use the current divider rule to express IB in terms of II or vice versa. Let's do that. So using current divider rule, all right. So we can write that IB is just the larger current multiplied by, okay, multiplied by what? Well, we want to know what IB is, so it's going to be R prime divided by R prime plus ZB. Okay. Okay. So therefore we can write in terms of II because we want to figure out what II is. We're going to use II in various other places. So therefore I is equal to IB times well, basically the fraction here ends up on the other side, so it's going to be R prime plus ZB at the top divided by R prime. Okay, so that's our expression for II. All right, so let's work out the rest. Let's have a look at VO. All right, so what is VO? Well, so VO is the voltage across the output, and this is a relatively straightforward Ohm's law. You know, V equals I times R. R in this case is RC. Okay, because that's the voltage that we can. The resistance that we can see from VO, and the current through it is IO. Right. So we can write again using Ohm's law that VO is V equals IR. So it's going to be IO. Well, not quite IO actually. So IO is drawn here as flowing from bottom to top. Well, VO is also positive uh, on the top side. So if you want to use IO in the same direction as what it is right now, then VO will be a negative value. So if you want a positive VO, we have to reverse the direction of IO by placing a negative in front of IO. So that's what we're going to do. Negative IO. So that means it just means that we want the current to flow the other way to get a positive value for VO. All right, times RC. All right. Okay, so that's that. Okay, now we can replace IO right now with beta IB because that's what it is. So then finally you're going to get a negative beta IB. Sorry. Okay, negative beta IB times RC. All right, so that's our VO. All right, so let's have a look at VI. VI is the input source, input voltage. And again, we're just applying the same principle as earlier for VO, i.e. Ohm's law. So what we're going to get is VI is going to equal to II. Yeah, that's the input current going in, into the network for VI times what? Well, it's going to times the combined impedance of all three things that we have here. So you have like R prime parallel with ZB, all right? So that's the resistance. So it's going to be R prime parallel with ZB, okay? Okay, so we can expand this a little bit, of course, by substituting II, which is equal to this, into here, and then expanding this parallel term, right? So let's put IB first, okay? And then we expand out this parallel expression, right? So which is going to be R prime times ZB divided by R prime plus ZB. Okay. All right. So you should be able to see quite clearly some of the terms will cancel out. So for example, R prime here would cancel out with this R prime, and R prime ZB, this entire bracket, cancels out with this entire expression. So then what's left is just going to be IB ZB, right? So it's going to be IB ZB, right? So so that's the expression for VI. All right. So now that we have all four of those terms, intermediate terms, IO, II, VO, and VI, let's work out what we really wanted to know, which is ZI, ZO, AV, and AI. So let's work out what ZI first. ZI is the input impedance, and it's shown here as seen by the signal source. It should be obvious by now. What it should see are these three impedances, R1, R2, and ZB. So I can write straight away ZI is just simply R prime parallel with ZB. Oops, became bold. All right, so that's done for ZI. Okay, let's have a look at ZO. Well, what is ZO? Well, ZO, every time we work out the output impedance of a circuit, we always zero the signal source. So we need to zero VI. Now, when you zero VI, then basically the top part is connected to the bottom part, meaning that they are at the same potential, i.e. 0 volts, which means there will be no current flowing through into the branch, right? Because it's all connected together. So it's going to end up as nothing at the bottom. So therefore, IB is going to be 0. Now, since IB is 0, then beta IB is also 0. Now, beta IB is a dependent current source, so therefore it is 0 amps. Now, 0 amps means it is an open circuit, right? So it's an open circuit. So that means there's a break here, meaning that the only thing ZO will see is basically just RC. So this is even more straightforward. All right. So ZO is just simply equals to RC. All right. So straightforward. So now let's go for AV. Well, what is AV? Well, AV, the voltage gain, is simply defined as the output voltage divided by the input voltage, right? So that's the definition of a voltage gain, AV. Well, we have an expression for VO. Oh, do we have an expression for VO? Oh, yes, heroes. Yeah, this is the expression for VO. Okay. All right, so we put it there, equals to that. And all of that is divided by VI. We have an expression for VI, which is IBZB. So IBZB. Okay. Oops. Okay. All right. So IB will cancel out with each other. Okay. And if you look at ZB, ZB actually has a beta term, right? So let's put ZB at the bottom there, and then we cancel out what can be canceled out, all right? So that's that. Let me just put that in first, and then grab a copy of ZB here. Whoa. Copy that. All right. So then come here, get rid of this, and put that in. All right. So then, okay, so it should be obvious that beta IB will disappear, right? So top and bottom beta IB will disappear. So this will go, and this will go. So then what you're left with is just negative RC divided by RE plus RE1. All right. And that's our answer for the voltage gain. And finally, the current gain, AI, is similarly defined as the output current, IO, divided by input current, II. All right, and IO is, we have an expression for IO, that's this one here. All that divided by II, which we also have an expression for. Okay, that's this one here. All right, equals 2. So you should get something like that. So IB will cancel out. R prime will be at the top. Okay, so ZB we can expand because ZB contains a beta. That's ZB, yeah. So this ZB contains a beta, so they will cancel out with the beta at the top as well. So let me just rewrite this part uh, with ZB intact for now. Okay, I think I need to hang on. Hang on. This is going to be a bit of a mess. Let me write again. So the bottom part is just going to be this. Okay. Oh my goodness, what is this? Hang in there. Okay, would that work now? Oh, wow. Okay, sorry. I just might as well type it again. IB R prime plus ZV. All right, so that's going to be the bottom part, and then multiply at the top with R prime. Okay. All right, so now let's substitute ZB into the equation. Okay, we cancel out. Let's just cancel out IB. Okay, so then you're gonna have at the top there beta R prime all divided by R prime plus ZB. So ZB is this term here. So let's just copy that. All right. Close it. I think that is it. Okay. So, well, the beta doesn't cancel out because obviously there's a R prime term at the bottom. So this is the final answer for AI. All right. So we've figured out the expression for ZI, ZO. ZI is here. ZO is here. AV is this, and AI is this. All right, thanks.